Welcome all. In this video, we will learn fundamental theorem of Galois theory. First of all, we will state what does it mean and then we'll prove it step by step in detail. Let K over F be a Galois extension and G be a Galois group of K over F. So K over F is a Galois extension and G is its Galois group. Then there is a bijection between subfields E of K containing F and subgroups of G containing identity. Okay, so every subgroup of Galois group is associated with some subfield of K containing F, and every subfield of K containing F is associated with some subgroup of Galois group. So this is a correspondence. Okay, so if I take E as my subfield, then I will take the elements of G which are fixing E. Okay, and if I'm taking H as a subgroup of G, then I will consider all the elements of K which are fixed by H, that is I will consider fixed field of H. So likewise this correspondence is defined from left and right, and these two correspondences are inverses of each other. That means if you have taken E, then definitely H is going to be the elements of G fixing E, and if you have taken H, then definitely E is going to be fixed field of H. So likewise, under this correspondence, these five things are satisfied. The first thing is that if E1 and E2 are fixed fields of H1 and H2, then E1 is contained in E2 if and only if H2 is subgroup of H1. Secondly, degree of extension of K over is coordinate of H, and degree of extension of E over F is index of H in G. Okay, which is depicted here diagrammatically, that degree of extension of K over is coordinate of H and degree of extension of E over F is index of H in G. Nextly, we know that K is Galois extension of F. Okay, but at the same time K is Galois extension of E also. Okay, with Galois group equal to H. That will be proved in the third part of this theorem. Then E is also Galois over F. So sub-extension of Galois extension is Galois. That is what we are trying to say here. So E is also Galois over F, and actually the condition is that it is possible if and only if H is normal subgroup of Galois group, and if this is the case, then Galois group of E over F is isomorphic to index of H in G, that is quotient group G by H. Finally, we will prove that if E1 and E2 are subfields fixed by H1 and H2 respectively, then E1 intersection E2 is fixed field of H1 H2 generated by H1 and H2, and E1 E2 corresponds to intersection H1 intersection H2. So now one by one we will try to prove these theorems. First of all, we'll prove this correspondence. Okay, so it's quite obvious that if you are provided with any subgroup H of G, then definitely we can find its unique fixed field, because we have proved in the earlier videos that if two subgroups are distinct, then their fixed fields are also distinct. Okay, so if you are assuming H to be a subgroup of G, then definitely it will have a unique fixed field. Okay, so that's why the correspondence above is injective from right to left. Okay, so we will think of it's from left to right. Now what happens, basically K is given to be Galois extension of F, right? So let me prove that first part. So K is given as a Galois extension of F, right? So K is a E is intermediate field, right? F is your base field, and K is Galois extension of F. So this is Galois extension, right? So by definition of Galois extension, it is going to be splitting field of some separable polynomial over F. So that's why K is splitting field of some separable polynomial over F. We have seen this in the characterizations of Galois extension as well. So let me assume that polynomial is f of x. So say f of x belongs to fx, right? Now f of x is a polynomial which is defined over f, right? But you can understand that all the coefficients of f of x are in f, but f is contained in e. So definitely f of x can be observed as a polynomial over e also. So f of x can be observed as a polynomial over e. Okay, and now K is a splitting field of f of x, right? So extension of K over E is going to be Galois, because K is a splitting field of a polynomial, separable polynomial over E, because we have shifted this separable polynomial over F 2 a separable polynomial over E, which is quite obvious because f is contained in E, right? So right now f of x is a separable polynomial over E, and K is a splitting field of separable polynomial over E. So that's why extension K over E is going to be Galois extension, right? And E is going to be fixed field of that Galois extension, because we have seen the characterization of Galois extension that K over E is Galois if and only if E is fixed field of its Galois group. So E is going to be fixed field of that Galois group automorphisms of K over E. Okay, so definitely it means that every subfield K of K containing F arises as a fixed field of some subgroup of G. Okay, as in this case particularly, what we have done, E is a splitting E contains f of x, and K is a splitting field of separable polynomial f of x over E. So K over E is Galois extension, right? So I can write here that K over E is Galois, and because of Galois extension, E is the fixed field of E is the fixed field of automorphisms of K over E because of the characterization of Galois extension, right? But automorphisms of K over E, that means automorphisms of K which fixes E, is nothing but a subgroup of G, that is automorphisms of K which fixes F, right? So it clearly indicates that E is a fixed field of some subgroup of G. Okay, this is going to be a subgroup of G. So this correspondence, clearly this correspondence is surjective from right to left as well. So it is a bijection, right? In this way we can see that this particular correspondence is a bijection, and they're inverses of each other. That's quite obvious to understand, because if I choose any subgroup H, I'm going to want a same fixed field, and if I'm going to take that fixed field, that field say subfield, then it's going to be fixed by H. So there is one-to-one correspondence between E and H. Okay, so this particular correspondence are inverses of each other. Now after proving that, okay, we'll show one by one the 5 statements that are already stated above. So firstly we will prove that if E1 E2 corresponds to H1 H2 respectively, then E1 is contained in E2 if and only if H2 is subgroup of H1. So let's prove this. So let E1 be the fixed field of H1 and E2 be the fixed field of H2, right? Now firstly suppose that E1 is contained in E2. Okay, I want to prove that H2 is subgroup of H1, so I will consider one element of H2. So let sigma belongs to H2, right? Now sigma belongs to H2 and H2 fixes E2, so that means sigma of A equal to A for all A belongs to E2. But E2 is bigger field and sigma fixes a bigger field, so definitely it's gonna fix its subfield, right? So this implies sigma of A equal to A for all A belongs to E1, right? So sigma fixes E1, so this implies sigma fixes E1. Okay, and as sigma fixes E1, clearly sigma belongs to H1, so this implies sigma belongs to H1. So I considered element from H2 and I have shown that element is in H1, so this implies H2 is a subset of H1. But try to understand that H2 is a subgroup of G. Okay, so basically it will something like this. This is your H1, this is your H2, and this is your Galois group G. So right, H2, H1, G. So H2 is contained in H1, right? And H2 is a subgroup of G. So definitely H2 is going to be a subgroup of H1. So clearly this implies H2 is a subgroup of H1. Now conversely, we can prove that conversely suppose that H2 is subgroup of H1. I want to prove that E1 is contained in E2. So let alpha belongs to E1. Now alpha belongs to E1, E1 is fixed by H1, so this implies sigma of alpha equal to alpha for all sigma belongs to H1, because H1 fixes E1, so H1 fixes every element of E1, so it fixes alpha as well. So sigma of alpha equal to alpha for all sigma belongs to H1, right? But H1 is a bigger group than H2. So if bigger group is fixing alpha for every element of E1, then definitely it's gonna H2 gonna fix alpha, right? So that's why sigma of alpha equal to alpha for all sigma belongs to H2 as well. Okay, and that means alpha was from E1. Okay, but now H2 also fixes that alpha, so alpha belongs to E2 because fixed field of H2 is E2. So this implies E1 is contained in E2. So this establishes the first fact that E1 contained in E2 if and only if H2 is a subgroup of H1, right? Okay. After that, we will move to the next statement that we want to prove, that degree of extension of K over E is coordinate of H and degree of extension of E over F is index of H in G. Okay. So let's prove that. Firstly, what we know that E is the fixed field of H. Okay. So we know that E is the fixed field of H. We have seen one theorem in the earlier videos that if E is the fixed field of H, then degree of extension of K over E is going to exactly equal to number of elements in H, right? So this implies degree of extension of K over E is equal to number of elements in H, right? But as per the extension formula, what we have further, degree of extension of K over F is actually equal to degree of extension of K over E into degree of extension of E over F, right? But degree of extension of K over E is nothing but coordinate of H, and the degree of extension of K over F is coordinate of G, because F is fixed field of G. Because try to understand that Galois group of K over E is G. It is Galois group of this Galois extension, right? So that's why EF is going to be fixed field of G. Okay, so that's why degree of extension of K over F is going to be equal to coordinate of G. Okay, so let me just mention here clearly, degree of extension of K over F equals to coordinate of G. Let me mention reason here, because F is fixed field of G. F is fixed field of Galois group G. Okay, so now just put these values and you will understand that this implies coordinate of G is equal to degree of extension of K over E, that is coordinate of H, into degree of extension of E over F, and that implies degree of extension of E over F is actually equal to coordinate of G divided by coordinate of H, and that is nothing but the index of H in G. So this particular thing established the fact that degree of extension of K over is coordinate of H and degree of extension of E over F is index of H in G. Okay, now let's move to the next point. Now we are going to prove that every sub-extension of Galois extension is Galois. So firstly, we'll prove that K is a Galois extension of E, and then we'll prove that E is Galois extension of F under some condition. So firstly, let us try to prove that K is Galois extension of E. Now what is E? E is nothing but fixed field of H. So that is why E is fixed by all the elements of H. Okay, so let me write here, E is fixed by all the elements of H. All the elements of H. But actually, what are the automorphisms that fixes E? So automorphisms that fixes E are nothing but set of all automorphisms of K over E. So this is collection of all automorphisms that fixes E. Okay, H also fixes E. So H is gonna subgroup of this. So this implies H is a subgroup of automorphisms of K over E, right? So this implies cardinality of H is less equal cardinality of automorphisms of K over E, right? That's the one point. But we have already know that automorphisms of K over F is less equal degree of extension of K over F. So if we'll apply that result, then definitely we know that cardinality of automorphisms of K over E is actually less equal degree of extension of K over E, right? And this is true for every extension, right? And equality holds when this is Galois extension that we have seen in the previous video as well. So this is less equal degree of extension of K over E, but as I have told you that E is fixed field of H, so degree of extension of K over E is gonna equal to cardinality of H. So now we'll try to combine these two statements. The first is that cardinality of H is less equal automorphisms of K over E, and cardinality of automorphisms of K over E is less equal degree of extension of K over E, which is equal to cardinality of H. So if we'll combine this, we will find that cardinality of H less equal cardinality of automorphisms of K over E, that is less equal degree of extension of K over E, but degree of extension of K over E is again equal to cardinality of H. So starting point and end point of this particular sequence is same, so that's why all the middle elements should be equal. So this implies cardinality of automorphisms of K over E should be equal to degree of extension of K over E, and this particular statement exactly matches with the original definition of Galois extension, and that is why K is Galois extension of E. So this implies K is Galois extension of E.
Now let's move to the fourth part of fundamental theorem of Galois theory. It means that is Galois over F if and only if H is normal subgroup of G, right? And then next part is quite easy to prove that Galois group of E over F is isomorphic to G by H, because we have already proved that if E is Galois over F, then Galois group of E over F is exactly same cardinality, that is degree of extension of E over F, and degree of extension of E over F has same cardinality as that of index of H in G. So that will be established as an easy consequences of this theorem. But first of all, let's try to prove this. To prove this, we will start with a fundamental notation. So what I will do, first of all, suppose E equal to KH. Actually, E is a fixed field of H, right? So I will write E is equal to KH. Let me write it in bracket that it is fixed field of H, right? Now, let sigma belongs to G. What is G? G is nothing but Galois group of K over F. So basically sigma is an automorphism of K which fixes F. Now that means we have a diagram that K is extension of E is extension of F, right? And sigma is an automorphism of K. Now what will happen? I can restrict that sigma to E. That means I can shrink the domain of sigma from K to E. So I will have a map sigma restricted to E. And this map will be from E to sigma of E. And it will be embedding. Okay. And this embedding also fixes F because sigma already fixes F, right? So every automorphism of sigma from K to K can be restricted to embedding from E to sigma of E. Now let's try to prove its converse part. Okay, now conversely, what I will try to show that every embedding of E is nothing but a restriction of some automorphism. So for that, let me first of all assume some embedding. So let tau from E to tau of E be an embedding of E that fixes F. Okay, so diagrammatically we can write this particular statement as a diagram that F is my base field, then we have E here, and then we have K here. Okay, so I am taking a map tau from E to tau of E, right? And this is embedding, and this embedding fixes F. Okay, so the first point is easy to understand that tau of E is actually contained in K. That means it is a subset of K. So let's try to establish that fact. So for that, what I will do, I will take one element from E. So let alpha belongs to E. be n element. Okay, m alpha of x be the minimal polynomial, minimal polynomial of alpha over f, right? Now tau is embedding. Okay, tau also fixes f. Okay, so that's why clearly tau of alpha is also a root of m alpha of x. Okay, now we want to prove that tau of e is contained in k. We have already taken alpha belongs to e. Now we have to show that tau of alpha is contained in k. Okay, so for that, basically tau of alpha is root of m alpha of x and k is Galois extension of f. So k is a splitting field of some separable polynomial over f. Also, we know that if that is the case, okay, so under that case, we can easily find that if k is a Galois extension of f, then every irreducible polynomial over f which has one root in k has all its roots in k. So m alpha of x is also irreducible polynomial. Its one root is in e, means it is in k, right? So its all roots are in k. So tau of alpha will be also part of k. Okay, so let me just write that here. So since k is Galois extension of f, comma, every irreducible polynomial with root in k has all its roots in k, right? And just think of m alpha of x. One of the root of m alpha of x is alpha, and alpha belongs to e. E is subset of k, so alpha belongs to k, right? So tau of alpha is also one of the root, so tau of alpha also belongs to k. So this implies tau of alpha belongs to k, but alpha is a random element of e. Okay, so this implies tau of e is a subset of k, right? So that means let's complete this diagram slowly. So let me erase this line here. Okay, so now let me complete this diagram. So this is your tau of e. So tau of e is contained in k. Okay, so we have k here and tau of e is contained in k. Now what can we do? See, k, we have already seen in the previous part that k is a splitting field of separable polynomial f of x. Means k is a splitting field of f of x over f. Okay, f of x can be shifted to e. Okay, now when it will be shifted to tau of e, it will be tau of f of x, right? And k is gonna be fixed field of tau of f of x also. It is a splitting field of tau of f of x as well. Okay, because tau of f of x, tau is a homomorphism of e which fixes f. So that's why tau of f of x, all the coefficients will be fixed. Okay, so that's why if k is a splitting field of f of x, k is also splitting field of tau of f of x. Okay, so these two polynomials have k as a splitting field, and splitting fields are isomorphic. So we can extend this sigma tau to sigma. Okay, and this is automorphism of k, right? Now this is your automorphism of k, so it clearly means that tau is restriction of sigma. So every embedding of e is a restriction of some automorphism of k. Okay, so this shows that, or we can mention these facts here as a k is splitting field of separable polynomial f of x over f. Okay, so this implies k is also splitting field of tau of f of x over f, right? So we will have two splitting fields because as I told you, tau fixes f, so that's why k will be also splitting field of tau of f of x as well. So we can extend tau to sigma because we have two splitting fields, k and k. Splitting fields are isomorphic, right? So sigma is automorphism of k. Thus, let me write that fact here. So thus, every embedding of E is restriction of some automorphism of K. Okay, fine. So every embedding of E is a restriction of some automorphism of K. Now, we will try to establish the next fact, then when two automorphisms restrict to the same embedding. Okay, so suppose sigma and sigma dash are two automorphisms of K. Under what condition I can say that they restrict to the same embedding? So two automorphisms, sigma and sigma dash, restrict to same embedding, if and only if sigma inverse sigma dash is identity map on E. That means sigma inverse sigma dash fixes E. Okay, so that means sigma inverse sigma dash fixes E. So definitely that means sigma of E equal to E. Okay, so basically we can say that all the elements that fix E are in H because H is a fixed field of H. Okay, so this implies sigma inverse sigma dash belongs to H. So that means sigma dash belongs to sigma H. So if sigma is restricted to some embedding, all the elements in coset of sigma, okay, will be restricted to the same embedding. So number of distinct embeddings, so I can just represent this particular fact diagrammatically, that if suppose this is coset of sigma, this is your sigma H. If sigma restrict to some embedding say tau, then all the elements in this coset will restrict to the same embedding tau. So number of distinct embeddings is exactly equal to number of distinct cosets of H, okay, in G. So that's why we can write here that cardinality of embeddings of E over F is exactly equal to, because each embedding fixes F, right, is exactly equal to index of H in G. Okay, but index of H in G is already taken to be degree of extension of E over F, right? Now under what condition K over E is Galois? Now K over E is Galois if and only if set of all automorphisms of K over E has same cardinality as that of degree of extension of K over E, right? This is condition for that Galois extension. And when E over F is Galois, so we can replace this K and E by E and F. So okay, so now see, so E over F is Galois if and only if number of automorphisms of E over F is exactly equal to degree of extension of E over F. But here degree of extension of E over F is equal to embeddings of E over F. Okay, so that implies E over F is Galois if and only if number of embeddings of E over F is exactly equal to number of automorphisms of E over F. That means each embedding should be automorphism of E. Now embedding will be automorphism of E. That means E over F is Galois if and only if embedding is automorphism, that means it is onto as well. So sigma of E equal to E. Okay, then only it is possible. Now we want to find out what is the fixed field of sigma. E is a fixed field of H. Okay, so which subgroup of G fixes sigma of E? So it is not difficult to understand that sigma H sigma inverse fixes sigma of E. So I will write that part in some different color to understand. Sigma H sigma inverse fixes sigma of E, and that's quite easy to understand. That's not so difficult to understand. What we'll do, we will take one element from sigma of E. Okay, so say H of alpha, for example, sigma of alpha. Okay, so sigma of alpha belongs to, let sigma of alpha belongs to sigma of E, right? So sigma H sigma inverse, because H is random element of right, so sigma H sigma inverse of sigma alpha equal to sigma of H of alpha, right? But H belongs to H and alpha belongs to E. H belongs to H, alpha belongs to E, and is fixed field of H. So H of alpha equal to alpha. So this is again sigma of alpha. So that means sigma of E is fixed by sigma H sigma inverse. So I can extend that particular statements further. So this implies E over F is Galois if and only if sigma of E equal to E. That means their subgroups of G which fix them should be equal. So sigma of E is fixed by sigma H sigma inverse and E is fixed by H. So sigma H sigma inverse should be equal to H. And that means E over F is Galois if and only if H is normal in G, because sigma H sigma inverse is equal to H, that means H is normal in G. And if H is normal in G, the next part is quite simple to understand. E over F is Galois. That means Galois group of E over F, coordinate of Galois group of E over F is exactly equal to degree of extension of E over F. But degree of extension of E over F is nothing but index of H in G, right? So that is index of H in G. Okay, so index of H in G means number of distinct cosets of H in G, and Galois group of E over F has same coordinate, so they must be isomorphic. So Galois group of E over F should be isomorphic to G by H. So that is the point we wanted to establish. So that completes the proof of your fourth part. Now we will go to the proof of last part, that if even it corresponds to fixed field of H1 H2, then even intersection E2 corresponds to fixed field of H1 H2, and composite field even E2 corresponds to intersection H1 intersection H2. Now subgroup generated by H1 H2 is nothing but subgroup generated by H1 into H2. Okay, so we will prove it one by one. Let's start with first of all even intersection E2. Okay, so suppose E1 is fixed by H1 and E2 is fixed by H2. Okay, now let sigma belongs to H1 intersection H2. So this implies sigma belongs to H1 and sigma belongs to H2. So sigma belongs to H1, that means sigma fixes E1. Sigma belongs to H2, that means sigma fixes E2. Right? Okay. So what does it mean? That means sigma fixes both E1 and E2. Okay, so that means sigma fixes composite of these two. So sigma fixes E1 into E2 as well. Okay, so that's the first part. Conversely, if we assume that sigma fixes E1 and E composite E1 and E2, conversely, let me write converse here itself. Conversely, if sigma fixes E1 E2 implies sigma fixes both, sigma fixes E1 and sigma fixes E2. Right? Okay, sigma fixes E1, that means sigma belongs to H1. Sigma fixes E2, that means sigma belongs to H2. And sigma belongs to H1 and H2, that means sigma belongs to H1 intersection H2. So we can write fixed field of H1 intersection H2 equal to composite of E1 E2. So that's my first part. Secondly, I will try to prove that let me take now H equal to, let H equal to subgroup generated by H1 H2, right? And I will prove that fixed field of this subgroup is nothing but E1 intersection E2. So firstly, if sigma belongs to H1 H2 subgroup generated by H1 H2, okay, and if we take any x belongs to E1 intersection E2, that means then sigma of x equal to x, because x is in E1, okay, and x is in E2. Okay, so if x is in E2, then H2 fixes E2, and if x is in E1, then H1 fixes E1. So definitely sigma of x is going to be x again. Okay, thus E1 intersection E2 belongs to fixed field of H, that is subgroup generated by H1 H2. Okay, now to establish second part, what I will do, see, now H1 is subgroup of H. Okay, so this implies, from the part 1 of this theorem, this implies fixed field of H is contained in fixed field of H1. Similarly, H2 is subgroup of H. So this implies fixed field of H is contained in fixed field of H2. So fixed field of H is contained in intersection of these two. So fixed field of H is contained in fixed field of H1 intersection fixed field of H2. But fixed field of H1 is E1, fixed field of H2 is E2, so this is equal to E1 intersection E2. So fixed field of H is contained in E1 intersection E2, right? So that means we have established both ways that E1 intersection E2 belongs to fixed field of H, and fixed field of H is contained in E1 intersection E2. So this implies fixed field of H is exactly equal to E1 intersection E2. That is fixed field of composite generators, that is subgroup generated by composite of H1 and H2, is equal to E1 intersection E2. That proves our second part. So with this we come to an end of proof of Galois theory, fundamental theorem of Galois theory. I hope you must have understood this proof. Okay, proof started with statement of Galois theory, and we slowly established all the subparts of it. Okay, so what are the takeaways? So takeaways are quite simple. That let me just put up here some takeaways. So takeaways are quite simple. That means if K is Galois extension of F and E is intermediate field, okay, then K, fixed field of K is going to be singleton identity, E is going to be fixed by H, and F is going to be fixed by G. So it is reverse inclusion. Okay, so it is reverse inclusion. That's the first point. Secondly, if K is Galois over F, if K is Galois over F, then K is also Galois over E, and E is also Galois over F. Okay, but there are two conditions. Here degree of extension of K over E is exactly equal to number of elements in H, and here degree of extension of E over F is equal to cardinality of G by H, that is index of H in G. Okay, so that's why Galois group of K over E is equal to H, and Galois group of E over F is isomorphic to G by H. Okay, these are the takeaways which can be easily obtained from this theorem. Okay, further, fixed field of subgroup generated by H1 H2 is E1 intersection E2, and fixed field of intersection H1 intersection H2 is nothing but composite of E1 E2. So these all are the takeaways of this theorem. So with this I stop here. Thank you.